Hi everybody, welcome to another video in Calculus 2. We continue working with Taylor series. On the previous section, we do some combination of the power series or Taylor series. Add, subtract, multiply, and divide. Now we focus on the calculus, namely limits, derivative, and integral. We just do some basic example. Right, first, limits. I find the limit of this function as x equal to 0. So first I'm going to put 0 in here. That will be 0, cosine of 0 is 2, 2 minus 2 is 0. So we have 0 over 0. This is indeterminate. If it is indeterminate, we can use the Hospital rule. That's easy, right? Yeah, so that's certainly using the Hospital rule. This will be easy. Now we're using the power series though. Focus on the power series. First we represent cosine of x using a Taylor series. So we know that cosine of x is an even function. So it will have all the even power of x over the factorial. So if we will write that out, even power of x over the same even factorial. Yeah, for all those series, it might be a little more complicated, but sine, cosine, sine is odd, cosine is even. At least we know that. And then e to the x, we have pretty much all the powers. Anyway, so I'm going to put this series into cosine of x. Right, I will write this x to 0 power is 1, 0 factorial is also 1, 1 over 1. So this is just 1. I will write as 1 half x squared and 1/4. Sorry, not fourth. 4 factorial is 24. And 6 factorial is 720. That could go on forever. So that's the series for cosine. Subtract 2 over 3x to the 4th power. Now multiply them out, simplify, and then find the limit. Multiply them out, x squared plus 2. 2 and 1/2 cancel out. 2 and 1 24. 12x to the 4th. 2 and that will be 1 over 360. X to the 6th. And so on. Minus 2 over 3x to the 4th. Right. Simplifying x squared minus x squared plus 2 minus 2. So we get those terms left, and of course then a bunch of them. And this will be higher power than x to the 6. So it will be x to the 8, x to the 10, all the even power that are higher than 6 in the dot dot dot. Right, but I will split this over and then the rest of the series on over 3x to the 4th power. Then I did say that we split, right? One over 12x to the 4th, 3x to the 4th, and then add negative 1 over 360 x to the 6, and everything after that will have higher power. Everything after that will have higher power than x to the 6 over 3x to the 4th. Now simplify x to the 4th. 1 over 12 divided by 3. Divided by 3 is multiplied 1/3. I'm just going to say 112 times 1/3, which is 1 over 36. And then here I only cancel the x to the 4th. It's perfectly fine to leave 3 there. So I have 3 at the bottom. The x to the 4th will cancel out though. X to 6, x to 4th, x squared. And then everything after this will have higher power than 6. So certainly they'll have enough x to cancel with x to the 4 at the bottom. But it doesn't matter though. It will have high power of x. Now, so all of this will have x on the top. But x go to 0. So all of the x power of x go to 0. So the top here goes to 0. Divide by 3, still 0. So all of this go to 0, and we end up with 112 over 1 times 1/3. So that is 1 over 36. Right. So that. Next, when I bring out, I realize that this should be infinity. So don't worry, I change the note, post it on the Google Drive. Anyway, so what do we do here? If we put infinity in here, sine over 1 over infinity is 0, so kind of like sine of 0. Actually, sine of 1 over infinity, just that sine of 0. And 6x to the 5th, x go to infinity, so we kind of have infinity times 0 here. So that also indeterminate. However, this will be more complicated. So maybe we use the power series again. Maybe it helps. Right. So we're going to write the power series for sine 1 over x. So first, sine is an odd function. So we have all the odd power of x over the 7 factorial. Right, that's how I remember it. On the odd power but we don't have sine of x, we have sine of 1 over x. So we have put 1 over x into x. Right. 1 over 1, so we just have 1, so this is x. I just write 3 factorial is 6. 5 factorial is 120. And 7 factorial I think is 50, 40. And because I don't like it. So 7 factorial. Yep. Now we're going to put 1 over x into this x, all of the x's. One over x minus 1 over 6, 1 over x cubed, 1 over 120, 1 over x to the 5th. Look like this is enough, but let's just go one more terms. 50, 40, 1 over x to the 7. Now substitute that in here. Six x to the 5th. Now, the Taylor series for sine 1 over x. Yes. By the way, this will be also handy if you have on page 115 the table on the common Taylor series. Of course, in the engineering book, there will be a lot more than that. There will be for tangent, cotangent, all the trig function, inverse function, all kind of different things. Right. 1 over x cubed I can write as 1 over x cubed. One over x to the fifth. 50, 40. 1 over x to the 7. Minus 6x to the 4th. Plus x squared. And I forgot that there will be a dot 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 here. Right. Now multiply it out. Maybe something we can simplify. At x go to infinity. Right, multiply it out. That gives us 6x to the 4th. 6 and 6 cancel out. X fifth and x cubed cancel out. So that's just minus x squared. X to the 5th cancel out. 6 over 120 is 1 over 20. And next, that is 7. What is that divided by 7? I mean, divided by 6. 1 over 840. And then x to the 5th, x to the 7th, we have 1 over x squared. And then the next one, we will have higher power than x to the 7 at the bottom. So we just have dot, 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 knowing that whatever we have after that, we have x with the higher power at the bottom, right? X to the 7. The next one will be x to the 9. Cancel with this will be x to the 4th. So we're going to have all the power of x at the bottom after that. Cancel that, and we're left with this, the infinite series here. However, since x goes to infinity, what we have here is finite over infinity, because I said that a lot. Finite over infinity is 0. That one go to 0. Everything in the dot dot dot, we have x at the bottom, we also go to 0. So only thing that left is 1 over 20. Right. So it turned out to be nice. So, and you say, well, that convenient, right? Convenient where there's a lot of things to cancel. And you say, what happened if this is 3? And then the Taylor series will not work. We do not cancel the 2 and the 3 here, right? Now think about this. If this is 3, we just go ahead and put 0 in directly. We don't even need to do anything else. The fact that this one is in indeterminate, that means the numbers conveniently cancel out. Some of them conveniently cancel out. Just like in the Hospital rule, there's something that can cancel out. Right. So this, since the numbers sound a little bit too convenient, because it is in the indeterminate form, so that's how it works that way. On that one, not on this one, not in particular. But again, of course, if they don't cancel out here, then x go to infinity will go to infinity. Right, so that some example about the limits using the power series. So pretty much whenever we see the function, we can represent that part of the function by the power series. Now, something a little more interesting is when we have derivative and integral, especially integral. We'll use a lot of integral because usually we don't feel the need of using the power series in derivative, because usually we should be able to differentiate a lot of function, almost all function, a lot more than we can integrate. When we end up being, when we have to integrate something like this, then that will be a little more difficult. I mean, by difficult I mean impossible, because if we can try to find the integral, the indefinite integral for this function, it will be impossible. Nobody can. So in that case, we can only do the approximation. Anyway, now I'll verify that the derivative of f of x is equal to sine x is cosine x. So show that derivative of sine is cosine. Simple enough. Right, so let's write out what is the series for sine of x. Right. Once again, sine x is an odd function. We have all the power to an odd power to the same factorial, alternating of course we can do that, or we can use the summation form. K goes to 0 to infinity, -1 to the k power. Of course, you can just look at page 115. This is the Taylor series for sine. And then we have x to the 2k plus 1 on top, 2k plus 1 factorial at the bottom. And then cosine of x on the even power. The sign alternating, sorry. K equal to 0 to infinity, -1k. And then we have an even power, 2k factorial 2k. Right. So that's the power series, the Taylor series for sine, cosine. Actually, those are the Maclaurin series because that's centered at 0. Now all we do is just differentiate sine x, and that should be equal to this. Simple enough, right? So let's start. What we do is differentiate sine x. So I'm going to write derivative of the series in the expansion form. Or we can also write the derivative of the whole series in summation form. We can take derivative term by term, or we can take derivative as the whole series in summation form. Right, derivative of x is 1 over 1. Derivative of x cubed, 3x square over 3 factorial, 6. 5x to the 4th, 5 factorial is 120. And then for the series, now we just take derivative of x to the 2k plus 1. Because none of this have x in it, we only take derivative of x. So we still have the summation. Derivative of x to the 2k plus 1. We take out the 2k plus 1. and then original power minus 1. 2k plus 1 minus 1 is x to the 2k. And then 2k plus 1 factorial is 2k plus 1. And then times 2k factorial. Right? Remember factorial, just like when we just try to do some randomly, like 102 factorial is equal to 102, and then 101 factorial. I can just keep going 101, 100, and so on, all of which will be factorial of 101. So we can just write 2k plus 1, and then 1 less than that, and then 1 less than that in general. Those cancel out, and we end up with this. Notice everything will stay the same because there's no x in it. Now if we compare in the summation form, this is exactly equal to this verify that equal to the series for cosine of x, which is good. Derivative of sine x is cosine x. I said nothing new, but this time we use the series to confirm it. Right, by the way, when we write like this, we can write that, of course, exactly as the cosine series as well. 2 and 6 cancel out, 1 over 2 or 2 factorial. Find 120 or 24 at the bottom, which is 4 factorial. And of course that will be the same as that. So it's confirmed. Differentiate term by term, we also have cosine of x. So derivative of sine x equal to cosine x. Whether we take derivative term by term or whether we take derivative in the summation form should have the same thing. Right, and then of course there are a few more examples, but set 1 is good enough. Now we're going to use the power series to estimate this. Now this time we definitely have to use the power series. By the way, if you look it up online, this type of function is called the error function. I think we mentioned that before. Right, first, what is the power e to the x? Now, e to the x, we have all the power of x compared to the sine on the odd powers, cosine on the even powers. E to x have all the powers. So we can say x to the 0 over 0 plus x to the first over 1 factorial x squared over 2 factorial and it's the plus. It's not alternating series. We can write this as we're going to have all the power of x over the same factorial. This is for x less than absolute values. Of course, interval convergence. Anyway, of course, if we want to, we can write this as a more convenient way, more friendly, I should say. Of course, that's still the same. Right, now I'm going to write the power series for e to the negative x squared. So all we need to do is just put the negative x squared into this x, into this series. We're not going to work in this form because when we integrate this, of course we can integrate term by term, but in terms of calculation, we're going to work in term by term. So e to the negative x squared I'm going to put negative x squared into x. Right, Let's clear this up. 1 minus x squared plus 1 half x to the 4th (1 6). By the way, this will be minus. The reason the sign alternating now because of the negative. X to the 6th. And then the next one will be plus 1 over 4 factorial, which is 24 x to the 8, and then so on. But we usually don't need all of the terms, but we can go as far as we want to. That's the idea about Taylor series. We can do for the first few terms, and then we can, in spirit, we can do that for a lot more terms, as much as we want to. And then finally put it back into the integral. Plus 1 half x to the 4th 1 6. I think that's enough. Right. If we want more accurate, just add more terms. Right. Now all we need to do is just integrate that. I'm not going to even do that by hand. Right. Integral from 0 to 1 minus x squared plus 1 half x to the 4th minus 1 over 6 . Yeah, let's stop there. And we have around that much. Just curiosity though, how good is the actual? By the way, when I say actual, it's still an approximation. But here I'm enter the function directly. Right. So this is up to the first two decimal places are correct. So it's not bad. It's not bad. But actually we can, in the Taylor series, also on page 115, we actually not on here, but actually it is. So that is the remainder. We actually can find the maximum error of this, but in this case we just do the approximation. So we represent a function as a power series and integrate each term. If we want to, we can integrate each term, but I'm just going to use the calculator and we evaluate that. Having said that, if we have the calculator, then we're just going to do that directly. But that's not the point. The point here is we can write that as the power series as many terms as we want to, and then we integrate this function. We can integrate this easily. Right. So that will help us to integrate. Most of the time we just represent a function by the power series, and then we go from there. Right. Next. Now, so we have a function. We can write the Taylor series, the power series. Now what happens if we have a Taylor series, a power series? Can we write that as a function? Well, for this, we have to look at the list of the Taylor series that we have and try to find the common things. So when we look at this, The characteristic of this is it has k factorial at the bottom, so that's important. So we look in the Taylor series, which one has k 2 factorial at the bottom. Actually, only one. E to the x has the k factorial at the bottom, so we will keep that. So let's say we have e to the x is the summation. We don't need to write out all the term. X to the k factorial. So we certainly have k factorial at the bottom, which is perfectly fine. We have k on the top. The only thing that is not quite the same is the 1 minus 2x, 1 minus 2t. So we will substitute into this x. Then we have those two series. But if we put in this x, we can put in this x as well. This series can be given at a, and we're going to put that in for x. Actually, that's all we do. Yeah, so that's why we see a lot in all of the engineering book. They have something similar to this, which is a lot more, actually a lot more than this. A bunch of Taylor series, So we just quick reference. We just take a look at those. All right. Actually, that's all we do. Now, if we look at this, what will be the power series? So for that, we have k at the bottom and k equal to 1, right? So look at all of this power series. We have those two. We have k at the bottom. These two have k at the bottom. Both from k going from 1, which is good. But on this problem, we do not have the alternating -1 to the k plus 1. So we're going to use this because that's just x to the k on the top. So I'm going to write out from page 115. Negative ln of 1 over minus x is equal to, I'm just going to write the summation k equal to 1 to infinity x to the k over k. Yes, this is the series. It even have the same thing here. Not quite the same. This one is less than equal to. Sorry. Right. So compare this and this. What do we see that are the same? The summation are the same. K the same. The thing is not the same as we have t to the 5k or x to the 5k. Right. So t to the 5k can we write as t to the 5th to the k power, right? Can we? Remember, when we have the power to another power, we multiply those. And that's why we have that. Now, if we have x to the k, then obviously x is equal to t to the 5th, right? Now we just substitute x to t to the 5th into this x, and we're done. So the summation equal negative ln of 1 minus x. Instead of x, we have t to the 5th. So with that, when we have the series, we can find the function that's corresponding to it. It's not always the case though. Usually, I mean, I cannot just give you a random series and then ask you what is the function, because that's not possible. It has to have some certain forms, and so this is only a few of the common power series. Remember, with this example on the page 116, we're trying to derive the Taylor series for tangent of x, and this is the first three terms in the power of tangent of x. We certainly can do that. We can write these more terms if we want to, but to come up with the common, to come up with the summation for tangent of x is extremely difficult, and it is impossible at our level, because it requires something with the high level to write this in the general form, in the summation form. So that's why sometimes we can just write that for the few terms, and sometimes for engineering, that's all we need really, because sometimes if we just want to do the calculation, even though if we don't know the summation form, even though we don't know the summation form, if we know a bunch of terms, that would be good enough. And by the way, not only we know the bunch of terms, we know that using those terms, the maximum error can be that much. So we know we can estimate using a bunch of terms, and we know how good our approximation is. And in engineering, that will be enough. So that's why this Taylor series is very important. Right. But what you need to know in this chapter is how do we write the Taylor series. Have to know how to do a table like this, and then combine the Taylor series, take derivative, integral, and then how to combine the Taylor series. And of course, I'm not going to ask you to memorize all of this. On the test, you should have this with you, and on the final, there should be a formula chart to go with the test. There should not be a problem. Don't need to memorize this. I only memorize the sine x, cosine x, and e to the x, because one is odd, one is even, and e to the x will have all the powers, all positive, over factorial. So, yeah. Anyway, so usually this example, as mentioned before, the number kind of convenient, because if it's not convenient, then the Taylor series, they might not simplify. And for those problems, if the numbers are not like that, you can just put 0 in directly. But usually this problem are kind of very nice. I cannot just give you a random series and ask you what is the function. That's not possible. It have to have in some certain forms. Anyway, so the real application in Taylor series will require a lot more than what we know in this class. But I think we cover enough examples. Anyway, I will stop this section here. See you in another video in Calculus 2. Thank you for watching.